please.
Okay, thank you. I start. Yeah. Okay, so let me first briefly remind about classical recurrent sequences. So we'll have at least an idea what we try to uh, not generalize, but maybe to extend to the tropical world. So first I will, okay, maybe about the plan. Briefly, I remind maybe in 2 slides about the classical recurrent sequences, more precisely classical recurrent linear sequences. And then I will give a very brief introduction into the tropical world. Then I will reformulate the tropical recurrent sequences and tell few results. And then hopefully it would be in around half an hour, and then we'll have a break and according to your plans. Okay, so classical recurrent sequences. We start with the vector. Real vector, and we assume just without loss of generality that the first and the last coordinates do not vanish. And then what is the ZI recurrent sequences satisfying A if the following relation holds for any k? So it's uh, and okay, so just an example, a typical example is Fibonacci number, very well known, and the feature which is true in the classical world, but which will fail in the tropical world is the following: that if you say no first n uh, uh, first n coordinates of the recurrent sequence, then you can continue uniquely the rest of the sequence. So as for Fibonacci numbers, it is n equals to 2. So if you know z0 and z1, then you can continue the rest uniquely. Okay, and it is well known the description of the linear space of all classical sequences, recurrent sequences satisfying A. We define the polynomial with just with the coefficients being the vector A, defining the sequence, and this sometimes is called characteristic polynomial. And consider any root x, and then if x is a multiple root, well, okay, so then if we consider the powers of this root x, then they will this sequence will definitely satisfies A. This is a typical example. If say x is a multiple root, then the derivative is also a recurrent sequence satisfying A. It is a well-known thing which I just briefly remind. And moreover, if the multiplicity of this root x is m, then we can consider m derivatives, so up to the order m minus 1, and they will provide the recurrent sequences satisfying A. And the main proposition in this aspect tells you that that's it. So all the described recurrent sequences, they form a basis of the linear space of recurrent sequences satisfying A. So again, if you for any root x, you with of the multiplicity m, you have m derivatives. So together you will have the number of their elements in the basis will be equal to n. So to the degree of the polynomial, or simultaneously degree of the sequence, so the length of the vector A. And continuing our example with Fibonacci numbers, it's the Fibonacci numbers, the corresponding characteristic polynomial have 2 roots, and then they form these powers, they form the basis, and say Fibonacci numbers themselves, they are given by some linear combination of these 2 sequences. Okay, so this was just a brief reminder about the classical situation. Now I will provide a brief introduction into the tropical algebra. The main object of the tropical algebra is a tropical semi-ring, and it's endowed with two operations. I will denote them in this way: plus or multiplication in the circle. And the main source of the tropical semi-ring is a nodded semi-group. So mainly you have a semi-group with a linear order, so you can compare any two elements. And this induces, semi-group induces a tropical semi-ring with the operations where the multiplication operation is the group semi-group operation, while the addition in this semi-ring is just the minimum. Okay, and moreover, if you start not with a semi-group but rather with a group, you can talk about also the tropical semi-skew field with respect to the operation tropical division, which is the subtraction in the classical sense. And moreover, if you have an abelian group, then you can talk about the tropical semi-field. Few examples. Say we consider the non-negative integers, or you can consider non-negative integers added by infinity. They are the commutative tropical semi-rings. You can easily verify it. And in infinity plays the role of the neutral element of zero. And in its term, zero plays the role of the unit. Say if you consider not the non-negative integers, but all the total set of integers, then you can talk about semi-fields, because now you have subtraction, so which is, I remind, which is the tropical division. And an example of the non-commutative tropical semi-ring is the semi-ring of n by n matrices, say over the letter semi-field. Actually, any of them you can consider, and with the operation, multiplicative operation, which mimics the usual operation of multiplying of matrices. And this is non-commutative, clearly, as for classical matrices, and this is a tropical semi-ring. Okay, this was about the tropical semi-ring, and now another important object for us is the tropical polynomial. So to define tropical polynomial, we start with the monomials. So monomial is the first, the elementary object is the, so we start with the variable and we consider its power, say I power. And this is the monomial. Then we extend it for many variables by considering the powers of variables, tropical powers of variables. And so we can also tropically multiply by some coefficient A. And we can talk about its tropical degree in the usual sense, as in the classical degree. Actually, it is useful to consider both languages, classical and tropical. And so tropically, it is a tropical, say, monomial, but classically, it is nothing else but a linear function. Okay, then next, a tropical polynomial is excuse me, can somebody tell me how can I delete the menu bar which prevents me to see the last few lines? Do you have any idea?
I think the Alt key is able to toggle that.
Say it again.
The Alt key.
A key. Which key?
I think the suggestion was to press Alt, A-L-T.
A-L-T.
Yeah, like the button where these 3 letters. Not
Okay, yes, yes.
But
Yes, I press it, nothing happens.
do you have like view on the upper right corner, the view button? Maybe you can find
no, they are just on the okay, I maybe do the following. I put this bar up and this, okay, then I can see now. Okay, fine. Sorry. Okay, so
the last line on the slide ends with 2 different values of I, right?
Of J. Okay, fine. No, no, the problem was that on my screen the bar prevents me to see, for me, the myself, the last lines. But now I put now I put the bar up, and now I don't see the upper lines, but this is not so important. Okay, thanks. Sorry.
Well,
thank
okay,
you.
they are, they don't have overlap, so.
Okay. Yeah, for you it is not a problem. It's only was a problem for me. Okay, sorry. So tropical polynomial, as in the classical sense, we define as a tropical sum of the tropical monomials. Classically, this means that we consider minimum of linear functions. So classically, it is just a convex piecewise linear function. Okay, and so this was very similar to what happens in the classical world, but what really differs, and it's some psychological problem, at least at the beginning of studying tropical mathematics, is how to define the tropical zero. It is defined as follows. Okay, look, X is the tropical zero of polynomial f, of tropical polynomial f, if minimum in this tropical polynomial is attained for at least 2 different values of j. Okay, so in the geometric language, I talked about that tropical polynomial is actually classically is a minimum of linear functions. That means that these are points. So tropical zero is a point where the tropical polynomial is not differentiable, is not smooth. Okay, so that's what we will to have in mind. Okay, and now I will just because I'm not sure that many people see it familiar with the tropical mathematics. I will very briefly give some historical overview of historical sources, because tropical mathematics has appeared in many directions, and this is in some senses a sign of fundamental science when something appears from different sides. Okay, one side was from mathematical physics. So people studied differential equations, partial differential equations, and and to simplify the problem, what they did, they tried to simplify the arithmetic. So what they did, they replaced the addition by this operation. So now t is a parameter. It's like in quantum mechanics, they introduce a parameter t, and this is somehow a quantization. It's a quantum parameter. And what do you have by tending t to 0? You just see it's a maximum. And in a similar way, you change the multiplication, but then it turns to be addition. That's how they replaced the arithmetic. And I don't dwell on the details, but they claim that they simplified the problem essentially. And so somehow they when you tend t to 0, this is somehow dequantization, and then you come to the tropical semi-ring from this maybe exotic operations, and then from the dequantization and from the behavior of the equations and their solutions in the tropical world, they get some information about the behavior for the initial equations. This is one source. I do it very briefly, really. So another source is arises from algebraic geometry. It's a solving system of polynomial equations in Piezo series. So I remind that Piezo series is a series in with the powers being the rationals rather than integers, as in the power series. With a fixed denominator, and it is known that they form an algebraically closed field when field F is itself algebraically closed. And actually, it started with Newton. Maybe it was really historically the first source of tropical studying. What Newton did, in fact, he started with a system of polynomial equations F, I, and he tried to expand them in the what was maybe 200 years later called Piezo series. And when you do this exercise, just formally substitute this series in the equations and try to expand them. And the first thing you need to understand what is the leading coefficient. And then when you do this exercise, you will see that you need the cancellation of leading terms. In order to have cancellation, you have to cancel at least 2 terms. And this condition of cancellation just leads you to tropical condition. And it's really a tropical. So summarizing, in order to find the leading, now in our case the least degree, the least exponent, you need to solve a tropical polynomial system. That was really the source of the first source historical of tropical world. Another sources comes from the computer science. It's the following problem. So you say you have a graph with weights on the edges, and the problem is that for any k you want to compute for each pair of vertices, so simultaneously for each pair of vertices, the minimal weight of paths between I and j. Then this problem is equivalent to the following. You start with a matrix of the weights, Wij, and then you take its tropical k power, and you will exactly get this answer. And the last thing which I will mention is the problem of scheduling. So the problem is the following. You have several jobs I and several machines j, and they have the times of the execution of this job by the machine corresponding. And there are some restrictions, like the following, that some job I should be executed after job I0 should be executed after job I. Or maybe another, well, and then you denote by xij a starting moment of execution. So that's the problem of the scheduling. And the latter restriction is expressed in the following way. Okay. And so there could be another restrictions, say like one machine can't execute 2 jobs simultaneously, like this, and so on. This sort of restrictions then can be rephrased by some system which contains linear inequalities and mean and plus. Say like this: inequalities, mean and plus, nothing more. And these systems of mean plus linear inequalities is equivalent. It's not difficult to see that it's equivalent to tropical linear systems. And so, for tropical linear systems, there is a quite good algorithms, and this is really, say, practically used in composing the schedule of railways in Netherlands. Okay, and now because we will talk about linear system, tropical linear systems, I will just specify what is more maybe special for tropical linear systems. So tropical linear system is provided by a matrix A. Well, maybe another another thing which is difficult psychologically when you study first tropical mathematics is that a system of equations is not equation in the classical sense. It's not something equals to something, but it's just a polynomial. So this is already a system. And remind that on the one of the previous slides, I defined what does it mean root of the polynomial of the tropical polynomial. And we say that, okay, this system of polynomials has a root if, well, then if x satisfies, so is I remind this definition in the application to the in the situation of tropical linear systems rather than general polynomials. And that means that for any, so it's x is a solution if for any equation this equality to be the minimum is satisfied for at least two columns. So for at least two terms in the minimum. Okay, so this is the just the definition in the application for the tropical linear systems. So tropical linear systems, they really well, their study is the subject of the tropical linear algebra, and it is much more developed than the general tropical mathematics. And so we'll say assume that the coefficients say would be integers or infinity. And say maybe one example from the, I would not dwell into details of the tropical linear algebra, but maybe just one example of a tropical determinant. Tropical determinant is just we take the determinant and take it tropicalization. So minimum, it replaces the sum over all the permutations, and each product in the usual formula for the determinant we replace by a sum of the corresponding elements, and we ignore the signs. We ignore the signs because there are no signs in the tropical world. And so this is the tropicalization of the determinant. And we say that the matrix is tropically non-singular if this minimum in this formula is attained for a unique permutation pi. And so if this is the case, then the system, linear system, has no solution. If it is non-singular, then the system, which is a homogeneous tropical linear system, it has no solution similar to the classical situation. Okay, now because I don't much time, I switch survey on the tropical linear algebra, which is it's very nice. And now proceed to tropical recurrent sequences. So we start with a vector similar to the classical situation with the real vector. Now we can add the infinity, which plays the role of 0, I remind. And now we assume that first and the last elements are finite. So that is similar to not being 0 in the classical sense. And so we say that Y is a tropical recurrent sequence satisfying A. I should add linear, but I omit because I don't consider nothing else rather than linear recurrent sequences. If the following linear equations holds for any k. So this is very similar to the classical situation, but now we replace sum by minimum and the product by the sum. Okay. And again, if we consider the set of all tropical recurrent sequence satisfying they form a tropical linear space. Okay, and so some examples that if we consider the a equals to 0, 0, so the vector of two zeros, that's the simplest case, then you can easily see that then there is a, well, then first of all, there is a sequence of all zero satisfies A, but actually only the sequences which are constants, they satisfy A, nothing more, only constants. Because in this case, this condition satisfies this next term uniquely. If you consider, say, this sequence, the vector A of now of 3 zeros, then situation is more complicated. Then there are much more tropical recurrent sequences. So what you can do, consider all the consider any sequence of indices I0, I1, and so on, and in both directions, with the condition that the difference between two adjacent is at least 3. Then you can consider the following recurrent sequence, actually the enormous set of them. You put y for all to be 0 for all indices out of this I capital, and any non-negative for all I from this set. So there is enormous the enormous set, and you see that well, and one of the well, unlike the classical situation when I mentioned at the beginning, the first two n the first two vectors, they define uniquely the rest of the sequence. Now we can enormous set of the tropical recurrent sequences satisfying vector A, and one of our tasks would be to define the measure how many recurrent sequences do we have. So that's the our, yeah, and well, and now the very useful language for defining the vectors and sequences is the language of Newton graph and Newton polygon. So we having the vector A, we consider the points I, we plot the points I, AI on the plane. They correspond to vector A. And well, what they form, we sometimes consider call Newton graph. And if we now to each vector, to which vector A consider the vertical ray starting with this point, okay, so this is B, any B greater or equal than AI, and then so we consider this vertical rays, and we consider their convex hull. Then this is called Newton polygon of vector A. And polygon has two vertical unbounded edges and several, so from the left and from the right, and several bounded edges. And just one definition, which will be for the future, maybe for the second part of the talk, we call a tropical recurrent sequence I minimal if for any I one cannot diminish I while keeping the rest and belonging, well, and satisfying the property to be the tropical recurrent sequence satisfying A. So you cannot change any coordinate. Then we call it recurrent sequence minimum. And well, the set of all the tropical minimal recurrent sequences is not now necessarily a tropical linear space. So just an example, continuation of the example from the previous slide. Again, we start with the vector A of 3 zeros, 0, 0, 0. And then we have seen that such a vector satisfies A. So each third coordinate is any non-negative coordinate, but it's not minimal. one can diminish any positive coordinate. Okay. Okay, and now I will.
I wonder, maybe that would be a good place for a break, or not? What do you think?
Maybe if we have maybe if I will continue for 5 minutes, I will maybe give the main definition of the entropy
Okay.
and the main results, and then we can stop.
Okay, sounds good.
Because at the beginning we had some technical problems. So
Yeah. Okay, no
okay,
problem.
sorry.
5 minutes is fine.
Yeah. Well, yeah. So two slides more. Okay.
Okay, sure.
So now, look, before we consider the infinite sequences, and now we consider finite fragments with the similar properties. So we say, okay, a finite sequence satisfies the same vector A if the same tropical linear equations holds. So nothing, no difference, but now we consider finite sequence, and the same for minimal. Okay, and now we consider the set of all sequences of the length S. We call them ds, and respectively ms is the set of all minimal sequences satisfying A. Geometrically, well, and we are interested in their dimensions, ds small and ms small. And actually, because they satisfy tropical conditions, actually some linear inequalities, they are finite unions of polyhedra. Some in the tropical world they are called tropical prevarieties. Okay. And let's do the following. Let's take S equals to A plus T and consider two projections from S on the first R coordinates and Q on the last T coordinates. And then it's easy to check that the projection of ds is contained in dr. Well, it's easily to see because if the sequence satisfied all the equations, tropical linear equations, then its prefix would satisfy as well, and also its suffix. Okay, the same for minimal. And now the main definition. Well, from this to containment, we have the inequality for the subadditivity inequality for ds function, and therefore it is called subadditivity lemma in the ergodic theory. We know that the limit of the ds over s does exist, and the same for ms over s. These are some non-negative reals. In general, clearly at most one. So these are the main definition. Okay, so if I will continue one slide, I will tell main results, or you prefer to stop now?
Oh, that's good. Let's hear main result. That would be good.
Okay, fine.
A good point for the break.
Okay,
yeah.
fine. Okay, so let's come back to our example, which we considered before, of a vector of all zeros. Then the entropy equals to 1 over this fraction 2 over n plus 1, and the minimal is vanishes. Okay, and now we say that the vector A is regular if the set of all indices with the finite coordinates forms an arithmetic progression. Okay, and moreover, I remind that I are the points on the plane forming the Newton graph, but now moreover we require that they form a vertices of the Newton polygon. say so they are in the this all the points are in the vertices. So this is then we call the vector regular. Okay, then the main result in this first part is that the entropy vanishes if and only if the vector A is regular. And also we can continue so that if the vector is not regular, then we know already that then the entropy is positive, then it's moreover it is at least 1/6. Okay, we have the following example. For the vector 1, 0, 1, 0, entropy is 1/4. And actually, very quite recently, my student has proved that both bounds are sharp. Namely, that the entropy is always at most the entropy for the vector false zeros. And for the lower bound, it is always at least 1/4. So it's now sharp bounds for the entropy. Okay, so now I can stop. Sorry.
Yeah, thank you very much. I think that's a great self-contained first part. Maybe like if there are short questions, a longer question, let's leave to the second part.
Okay. Well, in the second part, I will maybe talk about the minimal sequences a little bit, because there are some interesting conjectures and considerations, and then I will come back to the some very general conjectures, both about sequences and minimal sequences. Okay, so we consider the case when Newton polygon has a single bounded edge. So it's, well, I don't have a picture, but it have a two vertical unbounded edges and a single bounded edge, which we can definitely suppose to be horizontal. Okay. And okay, so we assume that it's horizontal. So the P of A, so the Newton polygon has the following structure. It has two vertices at the end, 0 and 0, two zeros at the end for 0 and n, and the rest points are non-negative. Okay, then in this case, if you take a constant sequence, then it always satisfies A. And moreover, one can consider periodic sequences with period D, and sometimes they would be the sequences satisfying A, and we will call them trivial when they exist, because they really they are very similar to the classical classical sequences. So we will study a question when a tropical non-periodic minimal sequence does exist. That would be our main question for a few slides. Okay, and so we now consider the several particular cases. The first particular case is the following. So we still in the situation when there is a single bounded edge, and now we assume that all points of A lie on this single edge. That means that the coordinates are always either 0 or infinity. Well, and we denote by I capital the set of all indices with the 0 coordinates. And the following first result, that in this situation, this very particular situation, all the tropical minimal recurrent sequences are periodic if and only if I forms an arithmetic progression. So that the situation is like this: you have zeros on the some arithmetic progression, and the rest are infinities. And in the case when this progression has a difference d, any tropical minimal recurrent sequence also has a period d. So this is a very clear situation. Moreover, you can slightly extend this theorem when you now still have points, some points perhaps out of this edge, and but still the points on the edge do not form an arithmetic progression. Then you can conclude that again you have a tropical non-periodic sequence, because the points of the Newton graph out of this edge, they do not make influence on these tropical non-periodic minimal recurrent sequences. Okay, so now the next particular question we slightly extend. Again, we are in a situation when Newton polygon has a single bounded edge. But now the points A on this edge, they form an arithmetic progression with a difference 2. And the rest of the points, they are inside, strictly inside of the Newton polygon. Okay, so situation is the following. So the even points are zeros. So now and clearly n is also even, but the rest of the points are strictly positive. Okay. In this situation, actually the conclusion is similar to the previous theorem, that all the tropical minimal recurrent sequence satisfying A are periodic. Again, we are reminded we are studying the question when all the sequences are periodic, if and only if all the odd coordinates they are equal. So all the rest of the points, they also form an arithmetic progression. So now there are two arithmetic progressions for even coordinates and for odd coordinates. Okay, and maybe the last, because well, I wanted to continue actually to consider the edge with the arithmetic progression with the difference 3 and so on, but actually the calculation become more and more complicated, and this is the last case which I was able to compute till the end. And moreover, we now well, actually in this the answer is different, because we cannot express it we cannot express it only in terms of arithmetic progressions. And moreover, I will consider only the vector of the degree 3. So now we have the vertices actually of the Newton polygon with the zeros as before, and the two other coordinates which are positive. And say the first is the greater than the second one. Well, similar case, the opposite case is similar. Okay. Actually, I did not calculate the case when I equal till the end. It's a small open question for the student, actually. Okay, and now the answer, as we see from this theorem. Okay, so what is this theorem? That all the tropical minimal recurrent sequences are periodic if and only if the following condition holds: that AI is less or less equal to 2 times A2. And you see now the answer is indeed cannot be described only in the terms of the arithmetic progression and so on. So now it depends on the relations among the between the coordinates. Well, and so the problem which I don't see it's how to solve it. It's really I see to be difficult is how to describe the vectors A for which all tropical minimal recurrent sequences satisfying A are periodic. Because look, this is really all three cases which I consider are really very particular cases. Even in the case when the difference is 3, I don't know the complete answer. Only in the case when n equals to 3. So very short vector. Well, I don't know the answer to this problem, but still something positive information that I have an algorithm which tests when a tropical recurrent sequence well then the resist of the non-periodic tropical recurrent sequence. Okay, now we assume that we have a vector, and so that we know that we have again the Newton polygon has a single bounded edge. So we have 2 zeros at the ends, and the rest are non-negative. Well, and they are between 0 and some m. Well, now I have to exclude infinity. This is again some shortcoming of the algorithm. So I don't consider the infinite coordinates. Okay, and one can test existence of tropical non-periodic minimal recurrent sequences satisfying A within some unfortunately exponential complexity. And well, the questions, well, I don't know really how to handle the case of the infinite coordinates. So it's one open question. Actually, now I will mainly talk about open questions. And another open question is it possible to improve the complexity? Okay, if you so these slides are already on the screen. And now I will say a few words about the tropical minimal entropy, about the bounds. Okay, so we come back to our example, which we already considered on one of the slides. So on the ends we have zeros and in between there are 2 coordinates, and this coordinate, I remind you, this was a crucial condition between A2 and 2 times A1, and now we assume that A2 is greater than 2 times 1. And I remind you that this was the case when they exist tropical non-periodic minimal recurrent sequences. This was the case. So if this was an opposite sign, then they did not exist, and if this sign, then they exist. And in this case, the entropy I denoted small entropy, so entropy which is responsible for the minimal tropical recurrent sequences, it is positive. Well, this bound is not sharp, I guess, but it's at least positive. It's at least 1 over n9. If we consider now the situation which is opposite, then the small entropy, so which corresponds to the minimal recurrent sequences, is 0. And this is not by chance. So there is some connection between the existence of non-periodic sequences and the entropy. And so I put the following on our open question. Again, we assume that the Newton polygon has a single bounded edge. And the question is whether vanishing of the small entropy holds if and only if all the tropical minimal recurrent sequence satisfying A are periodic. So in the example, it is really indeed the case. Here in the first example, we had existence of non-periodic and the entropy was positive. And the second case, the non-periodic sequence do not exist and the entropy vanishes. And the question is whether it is always the case. Okay, another open question is the problem is that it's really some problem, because my guess would be that these problems all are difficult. I don't see any ideas for them. Okay, and look, now we consider the question. I remind that ds was the question of was the function of the dimension of the sequences of the length s satisfying A. And is it true that this function is linear in S for S from each arithmetic progression with some difference? So the conjecture is that there is some difference. And if you consider the arithmetic progressions with this difference, then function ds on each arithmetic progression would be linear. And well, if it were true, if this function were linear, then the leading coefficient of linear function would be the entropy. That is for sure. But the question is whether it is indeed linear on each arithmetic progression. And if it would be the case, then we could say that ds would play a role of a tropical Hilbert's polynomial. Just two examples in which I was able to calculate it up to the end. Well, consider our already very familiar in many slides vector of 3 zeros. Well, then the function of the ds function, so the function of the dimension, is just the ceiling function of s over 3. So it is exactly what I suppose here. So here the difference is 3, and at the arithmetic progression 1 modulo 3, it jumps. It jumps, and for the rest it stays unchanged. And then another example, when actually for difference for degree 2 of vector, there are only two possibilities. Or either we have three zeros, so all 3 points are on the edge of the Newton polygon, or 1 point is inside, or there is another possibility when say 0 minus 1 0, but then the entropy is 0 and the function actually the ds function is a constant. Well, I did not mention it here, but in some sense it's a trivial situation when the in the main theorem from the first part of the talk, the Newton polygon is regular. So now it is non-regular, and then we have a positive entropy. So here entropy is 1/3. Here entropy is 1/4. And then again, in the second example, we have the situation which justifies the hypothesis from the problem, from the second problem, is that we have a difference 4, and for the arithmetic progression 1 modulo 4, we have a jump of the dimension. For the rest, it is unchanged. So this is the problem. Okay. And now I say a few words because it's the very beginning of the story for the multidimensional case. So before we considered one-dimensional case, so the sequences, the tropical recurrent sequences in one dimension. But now we proceed to the many variables. Okay, so now now the vector is a vector in the living with the support on the lattice, m-dimensional lattice, and the set of multi-indices are called the support of A. And the tropical multi-dimensional recurrent sequences, it's again similar to the classical situation. It satisfies if for any k, so for any multi-index k, so for any actually shift, for any shift k, the tropical linear equation holds. So it's just a generalization to the multi-dimensional case of the recurrent sequences. And again, we'll define the entropy. But now it's more complicated because we are living in the many high-dimensional space. So what we do, we consider some integers k1, km. We consider parallelepiped with the sides q1, qm. And in a similar way to the one-dimensional case, we denote the set of sequences with the support in this parallelepiped by d capital Q1, Qm. And for the m, in the similar situation, we consider the set of minimal sequences. So we just generalize from the one-dimensional case. And again, similar to the one-dimensional case, we denote by d small the dimension of the set. Again, d capital would be a tropical prevariety. It satisfies some linear inequalities. So it's a union, finite union of polyhedra. The similar for m. M small is the dimension of capital. Also, it is a tropical prevarieties. And again, we can say that the following limits do exist. So the entropy, so which is a limit for dimension over the volume of the parallelepiped, and the similar for m capital. So it's again volume over the volume parallelepiped, dimension over the volume of parallelepiped. It's the limit do exist, and we call them tropical entropy and respectively the minimal tropical entropy. Well, now not much is known. Some bounds. So if the support of A is contained in a cube with a side R, then we can separate from 1. Actually, it's trivially entropy is between 0 and 1, and we can separate from 1 if we know something about the support. Well, and in the example, our favorite example, when all coordinates are zeros in some cube with a side R minus 1, then the entropy is at most, it's very similar to the one-dimensional situation, 1 over d over r to the power m. Well, and now I want to formulate actually the last main conjecture in this direction. Well, we start with the tropical prevariety. So tropical prevariety is so it's similar to the classical situation. We start with some ideal, some now tropical ideal, and we consider the set of the points satisfying this ideal, and this is called tropical prevariety. Well, it differs from tropical variety, but I don't dwell on this now. And let's consider its radical. So all the polynomials, all the tropical polynomials vanishing on it. We call it radical. It's similar to the radical in the algebraic geometry. So all the polynomials tropically vanishing on it. And the following problem I put that if we now consider tropical radical ideal, okay, then my conjecture is that actually the entropy vanishes. This is not so vanishing of the entropy is not always true if you consider the non-radical ideals. There are some examples. Well, I don't give them here, but so they published in one of them. I don't. It's not a. It's at least some in the archive somewhere, so I can provide these examples in this archive paper if somebody's interested. And this conjecture has some two justifications in the very, very small particular cases. Okay, this is true when we consider the zero-dimensional, so tropical prevariety consisting of a few points. Then this is true. In another case, when V is a tropical plane curve in the plane, so in the plane, and given by a tropical polynomial with a extended Newton polyhedron having a single bounded phase. Actually, what is the extended Newton polyhedron? This is a very similar to what I talked about the Newton polygon, but now we have a tropical polynomial, and to each point into variables, and to each monomial of it, we attach a point in the three-dimensional space. So it has coordinates of the powers, so of the powers of the monomial, of the exponents of the monomial. So these are two coordinates and one coordinate for the coefficient. And this is called extended Newton polyhedron. And then we do the same game as we did with the Newton polygon. We consider for each point a vertical array. And then we take all these rays the convex hull, and this is called extended Newton polyhedron. And we assume in this theorem, it's unfortunately it's an assumption that it has a single bounded phase. Actually, geometrically, that means that the tropical curve of this Newton polyhedron has a single vertex. It has a single vertex and several edges. Well, and so in this case, in this very, very particular case, with long efforts, I can prove that indeed the entropy vanishes, and conjecture is that it always vanishes for any tropical radical ideal. So I finish with this. Thank you for your attention.
Thank you very much. So now we have time for questions. Please just unmute yourself and ask, or type them into chat, and I will read them. So then perhaps let me start. So also I know that there is a differential tropical differential algebra. Is there like a similar entropy phenomenon there, or for some reason it doesn't show up?
Well, what does it mean? You know, here we are, well, actually, look, what we are talking here, so tropical, well, actually, even in the classical world, tropical recurrent sequences, they correspond to the differential equations with constant, linear differential equations with constant coefficients. Mm-hmm. So you can do the similar game in the differential equations. Actually, you can actually what I did, I have extended this to what I called holonomic tropical recurrent sequences. So you now these are they satisfy. Well, actually, they correspond to linear differential equations now with polynomial coefficients. Well, and here also they appear the entropy. Actually, and entropy appears everywhere when you are talking about some infinite dimensional space, which you can, which is growing by finite its fragments, and then you ask how fast these fragments grow. that's what an entropy actually describes. And if you have the situation like this, you can always talk about entropy. If you ask about the tropical differential algebra, then the problem is different. Actually, recently, maybe you know this story, they proved the fundamental theorem. So they are you ask when a system of nonlinear differential equations, usual differential equations in partial derivatives, it has a solution in power series, and then the answer is in the tropical terms. So if it has a tropical solution, the tropicalization of ideal, then you can lift actually this solution to the power series solution. So actually they study completely different question, but actually you can continue always this entropy stuff when you have a sequence like as I say, infinite sequences with a growing finite subfragments.
Okay, I see. So yeah, so in principle we can turn this way. Other questions, comments? Okay, let me just ask one more question. So you were saying that you were able to compute like this dimension polynomials only for like not so large sequences. Do you think it's possible just to program and to run on a big computer and get more data, or there is no actually implementable algorithm to get more data on this?
Well, I don't know. Actually, one my student whom I mentioned, he is now trying to compute something. But look, well, I mean, surely you can compute finite fragments. So you consider the sequences of any not surely not too big finite dimension S, and compute the corresponding tropical prevariety of all recurrent sequences of the length S satisfying a vector, and then compute its dimensions. So this game you can do, but then say to compute entropy, you need to know the behavior of this function at infinity, because you consider the limit. But you can, yes, you can maybe consider maybe some conjectures looking at the finite fragments of it. And actually say to to justify what I asked about the periodicity and so on. But then you wouldn't be sure that you are going to the infinity. You can stop. You have to stop at some point, at the limit of your computational power.
Okay, good.
Because look, these questions are really about infinity, behavior at infinity.
Yeah, I understand. So you cannot compute them like exactly, but you may be able to still to conduct some experiments to at least to get.
Yeah, sure.
Intuition. Okay,
sure.
Okay, yeah, fair enough. So there is a question in the chat asking about a connection between this entropy and entropy in information theory or thermodynamics. So if you could.
Well, actually, this entropy is more okay. Right, there are many. Well, this word entropy is used in many senses. This is more close to the entropy from the ergodic theory. Remember that in the ergodic theory, what you do, you have some transformation, and then you consider its iteration, and then you look at its measure of the powers of a transformation, how they intersect with some initial set. So you take some set, you consider its traces, by the transformation, by the iteration of the transformation, and then you are interested in the measure of the measure of the intersection of the transformation of the set with the initial set. And and again, you take this limit so you take this measure or divide over the s and so on, and take the limit, and then that's what is called the entropy of the transformation in the space with the measure. So this is from the ergodic theory. From the thermodynamics, this is a little bit different. And the entropy, but I would say that in the thermodynamics, this is a measure of chaos. Well, and in this sense, this is similar to the ergodic entropy, and also in the information entropy, because in information theory, entropy is also the measure of chaos. So I would say that the cover of the whole of all the measures of all the concepts of entropy in different I would say in the different branches of science is the measure of chaos. But in the thermodynamics, you measure the chaos of molecules in gas, say, and in the information, it's a chaos of the entropy of your knowledge, and so on. He is the chaos of the sequence, and the ergodic theory is the chaos of your transformation in the space with the measure. So that's the that's the common cover concept of the entropy in all these different sciences. I'm not sure that my answer is very satisfiable. But at least
no. So the person who asks, John Hay, says thank you. So yeah, I hope it's good. So any other questions? Just unmute yourself or post them to chat. Okay, so then if no questions, then we thank the speaker again. And yeah, hope to see everyone in a week. It will be a talk by Kikazal from Han about algebraic solutions to differential equations.